Thank you. So I'd like to thank the organizers for the invitation to speak here. I'm very happy to be back at this beautiful conference venue and to have this opportunity to talk about some recent work. So what I'd like to do is describe some work in progress, the goal of which is to give a rigorous definition of contact homology. So let me begin by saying what that means. So contact homology was due to Ali Ashberg, Giventhal, and Hofer around 2000. So it's defined as follows. So let's fix a contact manifold Y with a contact form lambda. And I'm going to denote by P the set of Rabe orbits. This means all Rabe orbits, possibly multiply covered. I'm going to assume that lambda is non-degenerate. So all the Rabe orbits are non-degenerate. That is, the linearized return map has no fixed vector. So in this setup, we want to consider holomorphic curves in the symplectization R cross Y. So in particular, or more specifically, we consider holomorphic curves of genus 0, which are asymptotic to some Rabe orbit gamma plus, exactly one positive end, asymptotic to some Rabe orbit in P, and any an arbitrary number of negative ends, asymptotic to some Rabe orbits gamma minus in P, in genus 0. Okay, so maybe I should say what almost complex structure we're using. So we'll choose an almost complex structure on this manifold R cross Y, satisfying the usual conditions. We want J to be R invariant. J of ds should be the Rabe vector field of lambda. J should send Xi to itself, and J on Xi should be d lambda compatible. So once we fix a J, there's some holomorphic curves like this. And I'm going to let M of gamma plus, gamma minus denote the moduli space of such holomorphic curves. So then Ali Ashberg, Giventhal, Hofer made the following definition: contact homology of Y. Well, it's the homology of some chain complex. The chain complex denote by contact chains Y lambda, and well, it's the free. I'll do it over here. It's the free polynomial algebra generated by the good Rabe orbits. So in this setup, Rabe orbits come in two types: good Rabe orbits and bad Rabe orbits. This dichotomy comes from some reasons of orientations on the moduli spaces of holomorphic curves. And one can give some concrete description of when the orbit's bad, something about the index. But anyway, so we take the free Q algebra on the good Rabe orbits. That is, the generators are just monomials on Rabe orbits. And we use the differential defined as follows. So the differential of some Rabe orbit gamma plus is defined to be the sum over moduli spaces of index 1 of the cardinality of this moduli space times gamma minus. Oh, and this is a differential on a polynomial algebra, we're going to make dj satisfy the Leibniz rule, so to specify it, I just need to specify it on algebra generators. Okay. Yeah. So let's take the. Maybe I need a 1 over this, but depending on how I define the moduli space, there's something like this. Yeah. Thank you.
And you assume that all the elements of gamma minus are good?
Yes. Yeah. Oh. Right. So there's a obvious problem with this definition as it stands is that this moduli space might not be cut out transversally. And then maybe this isn't finite, maybe d squared isn't 0. So the problem is how to define this cardinality when M is not transverse. So this is a problem I'd like to talk about. Okay, there's, let me say, in some cases of interest, one can achieve transversality by choosing generic J. There's recent work of Bao Honda and Hutchings-Nelson where they show for some interesting classes of contact manifolds, this definition is okay. For most contact manifolds, though, you have the usual. You almost never have transversality due to the usual problems with multiply covered curves.
So another starting question. If you have a simple ray orbit, you can look at its multiple covers, right?
Mm-hmm.
You just take the positive multiple covers. So is that right? So
Positive?
well, I mean, that you can go around them in either order, or you can go around them in either direction, or?
If it's negative, then then it's not a ray orbit. It's like the orbit of minus r instead of r.
Right.
Yeah, only in the positive direction.
Yes. To think it's a simple ray orbit. What you mean is it could be.
Could be multiply covered.
Multiply covered, and they have a direction. So
Yeah.
Positive.
Yeah.
Positive. Okay.
Yeah. Every simple ray orbit contributes the positive integer's worth of generator. Yeah. Right. Okay. So the answer. This is the theorem which is still being written up. Is the following. So there exists a non-empty set, capital theta, which depends on this triple y lambda j, along with, for all theta in capital theta, numbers, which I'm just going to call this. They're rational numbers. Okay, let's say just for correct index with d squared equals 0. So this means I define the differential using these counts. Okay. Stated like this, the theorem is vacuous because you could just take all the numbers to be 0. So I better state another property. Okay, so I don't know much about the numbers that you get, but I do at least know that if any one of these moduli spaces is transverse, then these moduli count is the night count. So now this seems to be a non-trivial statement. Okay, remark is that together with being written with this result is sort of same thing for cobordism maps, etc. So and together with the cobordism maps and everything, you can check that this resulting homology is independent of lambda j theta. It depends only on the context structure. So the rest of this talk, I want to sketch the approach to this theorem and hopefully give some insight into the techniques used in the proof. Okay, so they're going to be 3 parts. So first I want to give a discussion of compactifications of moduli spaces. So far I haven't said about anything about how the moduli spaces are compactified. Second, I want to tell you how to construct something called implicit atlases on these moduli spaces, and then how to extract the virtual fundamental cycle from these atlases. Okay, so as I've already alluded to in writing this, the proof is going to use this notion of an implicit atlas and some accompanying a theory of virtual fundamental cycles. So whenever to prove any sort of theorem like this, which asserts that you can count moduli spaces which aren't cut out transversally, you want to use some virtual moduli cycle machine. And there are a number of such machines available in the literature. The ones which come to mind in particular are, of course, Kurenishi structures developed by Fukaya Ota Ono, and polyfolds developed by Hofer, Wasatsky, Zender. I'm going to use this machinery because it's the one I understand the best. There's also the Kurenishi atlases developed more recently by McDuff and Verheim. But okay, I'll use this one because it's the one I understand the best, and hopefully this shows that it's somewhat useful. Okay, so now let me talk about compactifications. So there's a standard way of compactifying the moduli space of holomorphic curves relevant for contact homology. It's called the SFT compactification. And what this is, I'll just say it in words, is the set of so-called holomorphic buildings, which look something like this. Where you have some stories, maybe look something like this. Stories are all symplectizations, and in each symplectization you have a holomorphic curve like this. And so there's this paper by Bourgeois, Eliashberg, Hofer, Wasatsky, Zender, and they show that, in particular, that this so-called compactification is indeed compact. Oh, this is a standard story. I want to also talk about a different compactification, which I'll just call embar. And this is, well, what is it? It's the same as the SFT compactification, except that each component of the domain, which I'll denote by C, is considered to be mapping to a separate copy of R cross Y. So what do I mean by that? So if I take this curve, and I take this component and this component, which are both non-trivial holomorphic curves and raise one of them and lower the other one, then that gives me a different point in the moduli space, in the SFT compactification. In this compactification, we consider those to be the same point. So this is somewhat, so there's a natural map here, which is surjective, just forgetting this relative vertical position. And in particular, this result here that implies that this space is also compact. So we can import all of the standard compactness results to this other compactification. Now, the strata of this compactification are indexed by certain trees. T, a tree looks like is something like this. So each of the edges is labeled with a Rabe orbit, including the interior edges. And each of the vertices is labeled with a homology class in H2 relative to the relevant Rabe orbits. Right, so I mean, the tree represents the dual graph of the domain. This tree represents a holomorphic curve, which looks like this. So in the SFT compactification, the codimension of a given stratum is given by the number of levels minus 1. There are two, so this has 3 levels as codimension 2, because there are 2 places you can glue. So there are 2 independent gluing parameters. In this compactification, the codimension is the number of interior edges. That is the number of sort of interior Rabe orbits where you can glue. So a remark is that the codimension 1 strata of this smaller compactification correspond bijectively with the terms of d squared equals 0. That is to say, if you expand d squared equals 0, you get some big algebraic identity relating the various virtual moduli counts, and it has a bunch of terms. They correspond bijectively with the codimension 1 strata of sort of the relevant moduli space here of index 2. The SFT compactification has a few extra strata, which in any reasonable sense are not going to contribute to the master equation. On the other hand, I find it convenient to work with this one just because they never come up and you don't have to deal with them. Yeah, so maybe I even have a time to draw an example of this. So I'll draw the SFT compactification. So let's look at a curve like this. So what I'm drawing here are the topological types of the curves in the various strata. So this is a top stratum. Here have some curve like this. And corresponding picture here is something like this. So the map here is precisely the map contracting this interval to a point. this is exactly the freedom of the relative vertical position of these two components. And this is the stratum which contributes 0.
Yeah. So just to understand the difference between the vertical edge and the horizontal edge is that they're breaking at different orbits?
Yeah.
If I understand right, so what you're doing is all trivial cylinders are being collapsed.
Yeah.
And then you're also kind of modding out by like your multi-R action on that.
Yeah, so one remark is that, okay, when you try to, so the SFT compactification has this nice property that it's always a manifold with corners. I mean, in transfer settings, at least. This smaller compactification, when you're talking about the moduli spaces which contribute to the differential, is a manifold with corners, because you have independent gluing parameters. But when you do this other compactification for, say, the cobordism map, then it's no longer a manifold with corners. The local stratification is a little bit more exotic. Nevertheless, the stratification is nice enough that everything works. Okay, so next I'd like to sketch the construction of implicit atlases on these moduli spaces, which are relevant for contact homology. Okay, so I already defined embar before, but let me just write the definition again slightly differently. So it's the set of U from C, from curve C to R cross Y, where del bar U is 0. Okay, understood to mean C could have multiple components, etc. Okay. So for this construction, I want to fix the following data. So one, I want a divisor inside Y. That is a codimension 2 submanifold with boundary. Just a smooth codimension 2 submanifold, and an integer. Okay, so there's going to be a third piece of data. But before I say what the third piece of data is, let me just make an observation that the first two pieces of data cut out an open subset of this moduli space. So if I look at the set of curves which satisfy, which are transverse to D, which have exactly R intersections with D, and have the property that when I add those intersections with D to C, it makes the domain stable. Okay, so this is a bunch of conditions, but this cuts out an open subset, which I'm going to call U alpha inside the moduli space. And if we have these conditions, then what do we get? We get a classifying map from this domain to the universal curve of genus 0 with points marked by this set. We have the punctures labeled by the positive ends, the negative ends, and the intersections with D. So here, this is just going to denote the universal family over the Deligne-Mumford moduli space of stable genus G curves with points marked with the set.
So D is how much over Y, not the Y of
Yeah, okay, so I mean D cross D, yeah. So this is what I mean. D cross R whenever.
Is it possible?
Is it possible?
Because you just compose U with projection, it might not be imagined.
Yeah. So I mean, this means that at those points it's an immersion. Yeah. I mean, I'm not asserting that these exist yet, but I will. I'll say something. Yeah. Okay. Right. Okay. So the last piece of data is I want a linear map from a finite dimensional vector space E into sort of C infinity sections over this universal curve. Cross with R cross Y, valued vertical 0, 1, differentials tensored with the tangent space of R cross Y. That should be R invariant. Right, so given this data, we can define a new moduli space, embar, which I'm going to call embar sub alpha. So here alpha stands for this choice of D, R, and lambda. So embar sub alpha is now, compared to embar, it's defined as follows. So again, I look at curves, and I look at elements of E, and I say that, well, first I want these conditions to hold. U should be transverse to D, exactly R intersections, and this stability condition. And now I also want this, what I call thickened del bar equation. Okay, so what's going on here? So there's a clear map which goes from this space to E, where I just forget everything except E. And the zero set of this map, forget about this, it's exactly this open subset of the original moduli space, exactly this U alpha. So the picture we have is the standard picture of a finite dimensional reduction or Kurenishi chart. So we have our moduli space, M bar, which is some potentially horrible topological space. We have an open subset, U alpha, and it's embedded inside this larger space, M bar alpha, as the zero set of a function. So let me make some observations. So first, okay, go back to, okay. So now I'm going to claim that every point of M bar is in U alpha for some alpha. So why is this? Well, so given a holomorphic building, like one of these, I need to show that there's a divisor which intersects all of these, all of the unstable components of the domain at transversely and makes them stable. So the unstable components only come in two types. There's planes and cylinders. Anything with at least two negative ends is stable. And you can check that this is true. The basic point is that the projection to y, if you look at sort of the projection onto C of the differential of U, you need this to be non-zero at some point. And if it were zero, well, the map would factor through a trivial cylinder. And that's a contradiction. So that's the first claim. The second claim, right, so to find some alpha for which a given point is in U alpha, I just have to pick D and R. So now I'm further going to claim that, so given a choice of D and R, it's easy to choose lambda so that any given point in U alpha is transverse, considered in this thickened moduli space embar alpha. So this again, given 1, follows for the following reason. The linearized operator at such a point is simply given by the linearized operator, the usual linearized operator plus lambda. And you can simply choose lambda to surject onto whatever you want.
So talking about again, there is a previous leader, and it's transversality. So that if it projects to Y, it's not imagined. You cannot choose P. So probably this is an exception.
So, and the domain of the multiple cover is then stable, or yeah. So it's okay. So we don't.
Okay, but maybe say a bit problematic because you don't have P.
Here.
And Z R is there in that case.
So I only have to stabilize the components of C which aren't already stable.
R is there, okay.
So R is for the whole curve. So R is the total number of intersections with all of that. So somehow if you have a multiple, if you have something of like multiple levels like this, you have a single divisor for all of the levels. So if they're, yeah. Yeah. Okay, so we can repeat this construction with multiple alphas. That has multiple choices of these triples. So what I claim is that this construction gives rise to a structure which I call an implicit atlas on this moduli space with index set A of t, which is just defined to be the set of all d r lambda for this given tree T. Okay, so I'm using some notation which I haven't explained yet. Embar of T, this is the stratum, the closed stratum associated to a tree T. So if you think about what that means, see that this is a disjoint union of stratus of type T prime for all T prime mapping to T. So this means a contraction of edges.
So is this index set of sufficiently many tuples that are bothered?
So I really mean all of them. Like it's a huge, uncountable. Yeah. So okay, I can make it a set by like equipping E with a basis or something, but which is to satisfy set theorists. Probably that's what you want to do, but it doesn't really matter.
But if you were building with lots of components, you picking one D, which is meant to do for all components.
Yes, yeah, in this definition, if you choose a D, it's for everything. Yeah. So this implicit atlas, well, it consists of a bunch of data, but the principal data is these so-called thickenings, embar of Ti for finite subsets I of the atlas. So they're defined exactly analogously to this moduli space up here, embar subalpha, except you have multiple alphas, and they fit together in a nice way. Let me just say that. Right. So in fact, and this goes back to Dusa's question. In fact, we can use a larger index set. We have an atlas with index set, I'll call it a bar of T, and this is the disjoint union of A of T prime over the subtrees of T prime. So that is to say, if I have a tree which looks something like this is T, and I pick some subtree, maybe consisting of these two vertices, then if I pick I can, if I want to, just pick an alpha for this subtree and then only impose this condition over that subtree. So we can use this sort of broader class of ways to thicken the moduli space. And it's important to be able to do this because this is what allows one to relate the atlases on different trees. Yeah. Okay, so some remarks about this construction. So first of all, this atlas is canonical in the sense that I didn't make any choices. That is, well, the index set consists of all possible choices, but well, I didn't have to sort of choose a finite covering set. You can just take all of them simultaneously. Okay, when stated this way, it seems sort of like a trivial observation. You can just do everything. You can take all charts at the same time. But the non-trivial part of this assertion really is in formulating the notion of an implicit atlas, the axioms, such that you can make such a universal construction. And this is sort of not so obvious. Okay. Now let me say a word about analysis. To verify that this is actually and satisfies the axioms of an implicit atlas and allows you to construct virtual fundamental cycles the way you want to, you need to show that if you have one of these thickened moduli spaces, and you look at the locus which is transverse, so I'll call it the regular locus, we need to show that this is a manifold with corners. And I'll qualify to say this to say I need it to be a topological manifold with corners. So there's this way of defining the virtual fundamental cycle of a space equipped with an implicit atlas, which only needs a topological structure here. And this is somewhat convenient when proving gluing theorems. If you want to put a smooth structure of a smooth manifold with corners, you would at least need to choose a gluing profile, and the smooth structure will depend on that. There are a few more estimates to prove. So there's some. I mean, you could say it's just a matter of convenience, but I think it's useful. Okay, so now finally, I want to tell you how you can define the virtual fundamental cycles, or coherent set of virtual fundamental cycles for these moduli spaces. Now, the word coherent here is very important. The reason that doing or defining Floer homology theories using virtual moduli cycle techniques is so much harder, or so much more complicated than sort of defining Gromov-Witten theory, is that you somehow need to make compatible choices on all the moduli spaces, do some induction, starting from the smallest strata up to the bigger strata. Okay, so given a space equipped with an implicit atlas, there's sort of a general theory of virtual fundamental cycles on a space X equipped with an implicit atlas. And I want to first summarize this general theory and then say how to apply it in this particular situation. So the general theory gives you the following. So there's a chain complex, which I'm going to call virtual cochains on X relative to the boundary. So this is some iterated cone of singular chains on these thickenings, X sub I. Those completely explicit definition is iterated cones of chains on some spaces. Now it comes with a push-forward map to the following. So here E is a vector space. This is chains on E relative to the complement of 0. Okay, so as we all know, this is the homology of this complex is the reduced homology of some sphere. The way I've made the grading, it's concentrated in degree D. So at least on the level of homology, this is equal to Z, and it's concentrated in degree D. So I'll follow notation and follow standard notation and denote that by Z shifted by minus D. So there's this isomorphism here, say in the derived category. There's also an isomorphism here, and this is non-trivial to show. There's a theorem which says that this chain complex is canonically quasi-isomorphic to the check cochains on X relative to the boundary of X. So you should think of this push-forward map as the chain-level virtual fundamental cycle. So what is a homology class? Well, it's a map from cohomology to the integers, up to torsion. If you work on the chain level, it really is that. So in particular, if you just look at what happens on homology, this gives you a map from check cohomology in degree D to Z, and that's the virtual fundamental class on X. Okay, so it turns out that you can use this as essentially a black box to extract the virtual fundamental cycles from the moduli spaces for contact homology, given these atlases that I sketched the construction of. So, okay, to do that, I need a definition. So we're going to let S be the set of trees T such that the moduli space is not empty. So this is a category with whose morphisms, T prime to T, are contractions. That is, you take some interior edge of T prime and contract it to get T. Something like this. If you have a contraction of trees, this corresponds to an inclusion of strata. This stratum of this tree includes into the closed stratum corresponding to this tree. Right. So now I'm going to make a definition. An S module is a functor f from this category S to another category. Along with compatible maps from tensor product of f of ti to f of this. So what do I mean by this? So this is the concatenation of some trees ti. So if you have a bunch of trees, say this tree and this tree, you can glue them together along pairs of input and output edges, like this. So this is a concatenation of trees. So maybe this looks like kind of a strange definition at first, but it's sort of encodes the basic properties of many of the objects that we've seen so far.
How do you see?
So it's any symmetric monoidal category. Yeah. Right, so examples. So if I look at the functor which sends a given tree to the moduli space, embar of T, this is a functor from the category S to the category of compact Hausdorff spaces, where the monoidal structure is product. So this is just really saying something very simple. You have this inclusion of strata for contraction of trees. And if you have a stacking of trees like this, there's a map of moduli spaces from the product of this moduli space times this moduli space to this moduli space. So this notion of an S module sort of encodes the basic combinatorial structure relevant for contact homology.
Do you define the monoidal structure to be all possible ways of concatenating?
So I mean, for any particular way of concatenating, you get such a map. So there's another one. Do I still have the definition? No. So I defined this index set A. I defined A bar of T to be the disjoint union of A of T prime over all the subtrees, connected subtrees of T. So this is also an S module, valued in the category of sets. Well, it's contravariant, and the symmetric monoidal structure is disjoint union. Right, so there's the functoriality of this VFC machinery tells you that this virtual cochain complex is also an S module, basically because this is an S module. So it's very important that this VFC machinery is functorial on the chain level, because that's what allows us to do things coherently between the moduli spaces. Okay, so I want to introduce two more S modules, and then we'll finish the sketch of the proof of the main result. So, okay, maybe I should use Q here. So here's sort of a very trivial S module from S. Target is again complexes. By this I just mean to every tree you assign the complex Q concentrate in degree 0. The functoriality maps are all the identity map. The product maps are all just product. Very trivial thing. And something a bit more non-trivial, which I'll call Q adjoin S. So I'll define that now. So Q adjoin S at a particular tree T is the free abelian group generated by all trees mapping to T. That is, we look at the moduli space of holomorphic curves of type T, and we look at all the boundary components of any codimension. And so take the free abelian group on that. And the differential is defined as follows. Differential, this is a sum with certain signs of codimension 1 boundary components of T prime. So it looks something like this. You know, you have, this is your moduli space. You take the free abelian group on the strata. Here I have 1, 2, 3, 4 strata. The boundary of this big stratum is this guy plus this guy. The boundary of this stratum is this, and the boundary of this stratum is this with the opposite sign.
There are some cases that there is a homology to extend this tree, right?
Yeah, so there's...
Even with that answer.
Yeah, so a given tree can have many automorphisms. So when we say a functor, that also includes the data of all those automorphisms. Yeah, and there are lots of denominators that show up in various places, which I probably haven't found all of them yet. But. Okay, so now this seems kind of, okay, so why do we care about this S module? So we have the following observation. So there's a bijection between choices of these virtual moduli counts satisfying d squared equals 0, and maps of S modules from Q adjoin S to Q. So this is another justification of my assertion that this notion of an S module really captures the combinatorial structure relevant for contact homology. So this is something about chasing definitions. So if you denote your map, say F from Q of S to Q, well, okay, I haven't said what the degrees of all these guys are, but if you make the right choice, sort of F of a given tree, well, you take this to be the virtual moduli count. And it's only non-zero for the guys of the correct index. And okay, why does it satisfy d squared equals 0? Well, you look at some tree of index 2. So f of t, since it's index 2, is 0. And therefore, its differential is 0. But this is a chain map. And so this is f of dt, and then this is the sum over codimension 1 guys, f of t prime, codimension 1. And this is exactly the sum of virtual moduli counts of codimension 1 guys on the boundary of t. So this proves that this is a bijection. so finally, let me sketch how you go from, how you apply this VFC theory to get the moduli counts you want. Right, so we have this S module, which is the so-called virtual cochains on moduli space relative to the boundary. Right, so secretly, we know this is quasi-isomorphic to check cochains on embar relative boundary. And there's a push-forward map, S star, to this space. But this space is just Z, or this complex is just Z, up to quasi-isomorphism. So as an S module, I'm just going to write Q here for this guy. And now the main assertion is that we can construct by induction a map from this S module to this one. Which sends a given tree to sort of the constant function 1 on this stratum. So what do I mean by this induction here? Well, the SFT compactus shows you that this category S is well-founded. That is, the set of objects which map to a given object is finite. And so you can construct a map like this by induction. This is the reason why we have to restrict to trees who have non-empty moduli space.
Induction is on what?
Induction on trees. From smaller stratum to the big stratum. Yeah. So right, a function is a check zero chain. So that's why this makes sense. Okay, so I think I'll stop here. Thanks.
I find your main assertion very cryptic. I don't understand what it has to do with the problem. Could you give a very simple example to explain what that means so that we can, when your S has got just 2 levels or something?
Yeah, let's see. So, okay, maybe I can start with like 0 levels. So, all right, we have this chain complex here, a push-forward map, say to Z. And let's suppose the virtual dimension is 0, because that's the ones where we're going to get out numbers. So there's this secret quasi-isomorphism with check cochains on X. Okay, so let's say there's no boundary. Okay, so on the level of homology, this gives you a map from the check H0 to Z. And what is this? This is integration with respect to the virtual fundamental class. That is to say, S lower star of the function 1 on X is exactly the virtual fundamental class of X. So this is some sort of generalization to the setting with boundary.
So how much of the work here is specific to contact homology rather than other flow homology theories?
Not much, I guess. I mean, there's the gluing, which is, whether it's specific to this or something else, you can decide for yourself. There's nothing special about this setup. It's standard gluing. And then there's the specific sort of combinatorial structure of the atlases, which is specific to this, but probably can be generalized. There's also the assertion that you can always stabilize with divisors. So that sort of requires the setting-specific arguments, but probably can be done in pretty general situations.